Greetings and welcome to the lecture notes for what I call Chapter 2, Part 2 of Chemistry 221. Chapter 2, Part 2 is over Chapter 2 and a little bit of Chapter 3. And you can see there's Chapter 3.1 and 3.2. So it's kind of a mixture. The basic idea, Chapter 2, Part 1 was mostly about the atom and what makes the atom. Also a little bit about the periodic table and where the things come from on the periodic table. For example, atomic number and atomic weight. This section, we're going to look more at the compounds. We're going to look at ways to name the compounds. We'll look at the three types of naming that are used. We'll also look at the mole concept as applied to compounds. And then finally, we'll use all these ideas to look at things called the empirical formula and the molecular formula, which is how chemists actually determine what's going on. So without further ado, let's get into it. But first, a bit of cheesy poetry. I'd like to tell you about poor Auntie May. Auntie Jane led to baby Nell what she thought was calomel. What the baby really ate was corrosive sublimate. Not much difference, even I must confess. Just one chlorine more and one baby less. Oh, sad, poor little baby. So this is incredibly stupid, and I apologize for the theatrics, but here's the idea. Calomel is mercury which is Hg, by the way, with one Cl. And when you have one Hg and one Cl, calomel is actually used sometimes in medicine for dysentery and stuff like that. On the other hand, if you have a mercury with two chlorines, you have what's called corrosive sublimate. And corrosive sublimate is a very poisonous substance. You don't want to do it. So when it said there on the last slide, one chlorine more, one baby less, if you mix up the formulas, you'll be in real trouble. So this very silly idea leads us into the reason why this is probably the most important chapter of Chemistry 221 through Chem 223, because it's on naming things, and just one additional atom can make a big difference in the reactivity of the compound. Oh, let's have another joke. What the heck? So this is one of my favorite ones because I think this is a little bit more understandable than mercury and chlorine. But anyway, if you start in the upper left and go along here, it goes, can I take your drink order? And the first chemist goes, I'm a chemist. I'll have just some H2O. And then the other chemist goes, well, maybe chemist, maybe not. LOL, I will have some H2O2. Now, just stop right there. H2O2 could be H2O as well, which is what this person means, but it could also be literally H2O2, two hydrogens and two oxygens. So you can see in the next slide that both of them say thanks, and then here you are, gentlemen. And both of the substances look like clear liquids, and they drink them down, and I'm sure it's very satisfying, but you can see the poor person on the right. And then finally the last person goes, idiot. Now, why this is kind of a joke, although a macabre joke, and I apologize for the sick sense of humor, H2O2, two oxygens and two hydrogens, is hydrogen peroxide, and it's used on cuts and sterilizing things and stuff, and it is useful as a substance. However, we all need to drink water, H2O, every day. So one additional oxygen here, as you can see, would actually kill someone, and H2O is something you have to have every day. So it's really important that we as chemists have a way to talk about these things with each other. So in this section, we're going to look at compounds, which are mixtures then of two or more types of elements into a distinct ratio. So for example, NaCl is a very common compound that's table salt or just salt. And table salt is always one sodium for every one chlorine. Now we're also going to look at some other weird things in this section. We talked a little bit about the atoms and how there's a number of protons. We're going to see that some of the elements exist in more than one of them together. All right. And buckyball C60 is an example of that. It's literally just 60 atoms kind of in a soccer ball formation. Ozone, which maybe you've heard of in the upper right hand corner, is 3 oxygen atoms. And that's quite different than the kind of oxygen we breathe. And we'll talk about that later. Finally, in the lower right is an example of an organic chemistry molecule. That's methane. That's CH4. We're going to talk more about those kind of compounds in Chem 222, but I am introducing it here just to show you the variety of things that you can get. Now remember that the smallest piece of a compound is a molecule, all right? And an ion is if you have something with fewer or more electrons than usual. And we'll talk about that in this section as well. So compounds are a combination of two or more elements in definite ratios by mass. What that means is that table salt, for example, is NaCl, and it's always NaCl. It's never NaCl2 or Na2Cl. The next part is important. The character of each element is lost when forming a compound. So, for example, we saw a video at the end of the last section. When you take pure sodium and pure chlorine, which would both kill us really quickly, it makes sodium chloride, which is table salt. So you can absolutely consume table salt, but you wouldn't dare consume sodium and chlorine. So the elements or the big things you start with are quite different than the compounds. And then just like we saw that an atom is the smallest part of an element, a molecule is the smallest part of a compound. If you break apart the molecule, it will no longer have the same properties as the compound, and it might do other cool things, but not what we wanted here. Here's an example of a formula, and we'll see lots of these coming up. Now, this is for a compound called glycine, and glycine is C2H5NO2. And what that formula means is that there are 2 carbons, 5 hydrogens, 1 nitrogen, and 2 oxygens. So notice that the number of atoms is placed in the lower right-hand corner. There's a picture of glycine, and that one's kind of color coordinated. You can see that the kind of blackish, grayish kind of atoms are carbon. The white atoms are hydrogen. Oxygen is a red, and nitrogen is a blue. And again, we'll see more of this here coming up. But the problem with some of these formulas is there's more than one way to write them. Now, the picture down there shows how the atoms are actually oriented in space. So scientists will sometimes, instead of writing it C2H5NO2, they'll write it H2NCH2COOH. And you can see they're trying to kind of follow the pattern on the molecule. So this part right here is the NH2, which is first. This is the CH2. Then there's a COOH. All right. So that's another way that sometimes people represent these. By the way, if you're noticing that this C and O has a different kind of connection, like 2 lines instead of 1 line, we're going to talk about that more in Chem 222. That's called a double bond. All the other bonds on this molecule are single bonds, and we'll see what that means future times. Chemists can also write that same formula in like 2-dimensional space. And this thing right here is just called a structural formula. And that's another way to do it. Now, a structural formula is nice because it kind of shows a little easier how the atoms fit together. It does show, for example, that carbon-oxygen double bond. But if you're using a program like Microsoft Word or Google Docs, which is kind of the dominant word processors right now, it's difficult to draw something like that. You'll need something like Illustrator or some program like that instead, or a special program to write chemical formulas, which do exist. So there's lots of different ways to write these. A structural formula is sometimes called a condensed formula, and all these ways are legit. Most of the time, we're going to write our formulas like this because they're compact, all right? But there are uses for the expanded versions as well. Here's, again, kind of an overview of some other ways to show. A drawing of glycine in a 2-dimensional kind of representation is right here. This one down here on the lower left is called the ball and stick model. In Chem 222, well, if we're meeting face to face, we will use a model kit, and the model kits essentially use like a ball and stick kind of system, and it shows the geometry, which will be important to us later. And then if you're more of a physicist or a chemical physicist, the space filling model model is actually the best way to represent it because it shows how the electrons overlap. Space filling, although they are probably the most accurate, are kind of difficult to see. So they're not used that much in just traditional kind of chemistry, but it does have uses sometimes too. So these are all ways of showing what glycine is. Here's another example. This is ethanol, another compound. Ethanol is actually drinking alcohol. Now, ethanol, if you look in the lower right corner, is CH3CH2OH. And all of these are ways to show that same thing, but with ball and stick space filling, or what's called a perspective drawing. But notice that they all have an OH. The upper two have a red oxygen, so it makes it easier to see. And then you have the CH2, CH3 parts on the end. Perspectives are sometimes used as well. They used to be really popular, but now the ball and stick with the right kind of programs are easier to make, but you will sometimes see it. In a perspective drawing, the little dotted lines, those are hydrogens that are going into the page of the screen, if you will, into the piece of paper. And these little kind of darker lines are called wedges. Those are coming out of the screen or out of the piece of paper, depending on what you're looking at it. So in this CH3, only this CH is actually in the paper. And then the little dotted dash line, that's going back into the screen. The wedge here that I put an arrow next to would be coming out of the screen. It's trying to show three-dimensional information. Here's different formula types too, and this will be helpful to us now coming up. Now, water, as we talked about earlier, is H2O, and that means 2 hydrogens and 1 oxygen. And water is going to be always H2O. It doesn't ever change its formula. Now, that's called a molecular formula. All right, that's kind of like a condensed version of the formula, and the molecular formula just says literally how many atoms are in the molecule of water. An empirical formula is the smallest whole number ratio of atoms. So whole number in chemistry almost always means don't have fractions. You can see here that water has 2 hydrogens and 1 oxygen. We can't break that number down by any farther. So 2 divided by 1 and 1 divided by 1, still H2O. Water has an empirical and molecular formula that's the same. We'll come back to this here in a little bit. Structurally, however, the oxygen's actually in the middle of the molecule and hydrogens are on the outside. So the structural version of water is HOH, and that'll be helpful to us too. Now, let's go back to that molecular empirical thing again. Hydrogen peroxide, the H2O2 that killed the chemist in that stupid joke I had earlier, that literally, the molecular formula is H2O2. So now you see maybe the joke and stuff. Oh boy. Anyway, the empirical formula is the smallest whole number ratio of atoms. So in hydrogen peroxide's formula, if you divide both of those numbers by 2, you're still going to get a whole number. So you divide both of those 2's by 2's, that's going to give you the HO. So empirical formula, smallest whole number ratio of atoms. And some molecules, like hydrogen peroxide, do have different empirical and molecular formulas, and some molecules, like water, share the same molecular and empirical formula result. The molecule itself looks like an HOOH when you figure it out, and that's something we'll do in Chem 222. So HOOH would be the structural formula, like what it kind of looks like in space. Ethylene, ethane, ethanol, and dimethyl ether are going to be great examples to take this a little bit further. Let's look at ethylene first, which, by the way, keeps your bananas fresh while they come up from Central America to North America. But anyway, C2H4 is the molecular formula. And if you would divide both of those numbers, the 2 and the 4, by 2, that's going to give you an empirical formula of CH2. So ethylene has an empirical formula of CH2. Ethane sounds kind of like ethylene, but it is different. It has more hydrogens. It's C2H6. So if you divide both the 2 and the 6 by 2, you're still going to end up with whole numbers. That's why ethane has an empirical formula of CH3. And you can see there how ethane kind of has an H3C and then another CH3 on the other side of it. Now, Ethanol and dimethyl ether, the last two examples, have the same molecular formula. They're both C2H6O. And because of the one oxygen, you can't make a one any smaller. The molecular and empirical formulas for those are going to be the same. But look at the structural formulas now. Ethanol has an H3C, and then it has a CH2 and an OH. So again, that's what it looks like. H3C first, CH2 in the middle, if you will, OH on the end. Dimethyl ether has an H3C, it has an oxygen in the middle, and a CH3 on the end. So ethanol and dimethyl ether have the same molecular and empirical formulas, but their structural formulas are quite different. So you can see hopefully here why all of these types, formula types, have uses in chemistry, and they're all going to be really important as we go through these sections. Okay, here's an example of a kind of question you might see. What's the empirical formula for P4O10? All right, and again, the idea here is you want to get the smallest whole number ratio of atoms, and whole number is important. If you divided the 4 and the 10 in that formula by 4, you'd end up with P1O2.5, which is D. But I'm going to let you know right now, chemists really do not like using fractions, no decimals, no fractions. So that wouldn't be a good choice in chemistry. Instead, if you take the 4 and the 10 and you divide them by 2, you would get P2O5. And those are both whole numbers. That's going to be the empirical formula. Again, empirical formula, smallest whole number ratio of atoms. Don't go to fractions. That's really important. Elements often exist in what's called an allotrope, which means it's the same element but different forms. And carbon is by far the best example of this. Now, probably you've all used graphite, which is the main ingredient of pencils, all right? It's like the lead. It's not lead at all. It's graphite, all right? But people call it lead. It's all right. It kind of bugs me as a chemist, but I'm not going to hold it against anybody. Anyway, graphite is a form of carbon. And if you look at that animation, there's like sheets of carbon atoms, and those sheets kind of wear off when you use the pencil and stay on the paper, which is kind of cool. Now, graphite is really cheap. You can go buy 100 pencils for almost nothing. Diamond, on the other hand, the one below it, is also carbon, but look at how it's rearranged. That's a three-dimensional structure. Diamond is quite different than carbon. Both of those are carbon atoms. All those little black atoms are carbon, but diamond is incredibly tough. And diamond, as you know, is also really expensive. It's very rare. It can be used for industry, for cutting things. It's one of the hardest substances known. So graphite and diamond are very common forms of carbon, but quite different, all right? Once in a while, Superman will like squeeze charcoal, which is basically graphite, and make diamonds out of it and stuff. So if you're a Superman fan, cool. And if you don't, you've better things to do with your time, obviously. Now, the one on the bottom is a relatively newer player. It's called Buckyball. The official name is Buckminster fullerene. Long story behind that. But anyway, that's the C60 thing. That's a third version, a third allotrope of carbon, all right? And it's really cool. Buckminster fullerene was named after this guy named Buckminster Fuller, who's really interesting. And also, there's other forms of carbon as well. Graphene is one of them that's really interesting. So all of these are carbon, but they're different forms of carbon. And you can probably imagine that reacting graphite is going to be a lot different sometimes than reacting diamond. So elements can have more than one allotrope, which means more than one version of the same element. Most of the elements, though, just exist as single individual atoms. So, for example, sodium and magnesium and things like that, just single. However, there are 7 elements that exist always as diatomics. So di is two atomed. All of these elements exist in pairs. And I like this little phrase right here, have no fear of ice clear brew. And it can be root brew. It doesn't have to be anything else, all right, if you're under 21 or 19 in Canada. But anyway, have no fear of ice clear brew is important because these seven elements that I've highlighted there in red exist as diatomic. Now, almost all the other atoms on the periodic table you can think of as monatomic individuals, but not these seven. So when it comes to hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine, all of those exist as diatomics, two of them. So that's where the have no fear of ice clear brew thing shows up. Now, some people like using the expression Honkelbrief, which is in the kind of star right there, and that's fine. And there's several other sayings like this, but these seven diatomics are going to be really important to us in the next section. So hang on to this piece of knowledge. These are going to come back. Again, I want to repeat though, most of the elements on the periodic table exist as single pieces. So if the element is not on there, then more likely than not, it's a single atom. So as I said, magnesium and sodium and helium and xenon, all right, all of those are not have no fear of ice clear brew. So you don't have to worry about it. But if you are dealing with oxygen or bromine, then you've got to think about it as a diatomic. There are other elements that exist in more than one piece. Phosphorus is a great example of that. Phosphorus, there's white phosphorus, red phosphorus, and even a black phosphorus. All of those are different forms, and you can see what they kind of look like right there. Sulfur exists in what's called an octamer, which is 8 atoms. And ozone, which is O3, 3 oxygens, is also another form of the elements with more than one. So you can see it's kind of interesting, but I do want to highlight most of the time the elements are just single atoms, but if you get to the have no fear of ice clear brew, then you have to remember those are pairs. Don't worry so much about phosphorus, sulfur, or even ozone for that matter. If you know the 7 diatomics and the fact that almost all the other ones are single ones, you'll be good to go. Ions are another important concept for this chapter, and an ion is just an atom or a group of atoms with a positive or a negative charge. And down there is a little picture, and you can see here how sodium chloride table salt is made. A sodium atom, all right? If you look on the periodic table, sodium is number 11. And we're going to see that sodium loves to lose an electron. And when that electron is kicked out, you went from 11 electrons. The neutral elements always have equal protons and electrons. It goes from a neutral atom to an ion with a positive charge. And the reason for the positive charge is that this thing lost an electron. It still has 11 protons. Remember, if you change the proton number, you change the actual type of atom it is. So it's still sodium, but now it has one less electron. So if you take 11 times plus 1, and add that to 10 times negative 1, it's like 11 minus 10, you're going to have a positive 1 charge. And we call that a sodium ion, or, as we're going to see in the next slide, a sodium cation. Cation is a positive charge. Now, electrons are pretty feisty and they don't stay by themselves for very long. So if sodium's going to be losing an electron, that electron has to go somewhere. And we're going to see that chlorine likes having an extra electron. Now, chlorine is number 17 on the periodic table. So it has 17 protons. And even after it does something with the electron, it still has 17 protons. But you can also see then that chlorine goes from the neutral version, and remember, neutral means protons and electrons are equal. It goes from 17 electrons to 18 electrons. So if you do the same thing we did with sodium, now you have 17 times plus 1 plus 18 times negative 1. You've got negative 1 left over. And that's where that negative charge shows in. This would be a negative ion, or fancy term is an anion. And we're going to see that it likes to be -1. If you take away an electron, it makes a cation. And again, a cation has a positive charge, so sodium forms a cation. On the other hand, you've got to do something with those electrons. If you add an electron or electrons, you create an anion with a negative charge. So cation means positive charge, anion means negative charge. And I have to warn you in advance that I am kind of a cat person. We have right now 2 cats that are kind of fun. They have their own personalities and stuff. You do not have to like cats to do well in this class. However, here's a quick way to remember cations especially. Cations, remember, are positive, so they have more positive protons than electrons. Anions, on the other hand, have more negative electrons than positive protons, so they're negative. So, cats have pos. Cations are positive. So if you're a cat person and you're into that, this is kind of a fun way. That's the little chemistry cat meme, which floats around the internet quite a bit. It always cracks me up. I have several jokes and stuff running around that people have made with the chemistry cat. But anyway, that's neither here nor there. The important part here is that cations are positive, anions are negative. And I don't have a cool expression for that. Sorry, but if you think of one or you see one, let me know.
When a magnesium atom loses 2 electrons, it becomes a cation.
This is an example of a magnesium cation being made. So it's a positive magnesium ion. Now magnesium is number 12 on the periodic table. So neutral magnesium means 12 protons and 12 electrons. But we're going to see here in a little bit, magnesium loves to lose 2 of those electrons. So the positive 2 cation forms Mg2+. And this is very, very common. We will see in a little bit with magnesium.
Fluorine becomes an anion when it gains 1 electron.
Fluorine, with 9 protons and 9 electrons when it's neutral, loves to get 1 extra electron. And when it does, it becomes the fluorine anion, all right, the F-1. So an anion has more electrons than protons. So fluoride, which is what we're going to call it, or a fluorine anion, has 9 protons and 10 electrons. So again, you can lose just 1, you can lose more than 1 electron, or you can also gain 1 or gain more than 1. So the question becomes then, like, what are the charges of the different species on the periodic table? And that's a great question. So we're going to talk here, first of all, about the positive ions, the cations on the periodic table. Now, in this section, it's very helpful if you have a periodic table. And I encourage you to write notes on it because they'll be helpful later on. There are 2 types of metals on the periodic table. All of the metals will be positive, but some of the metals, we know what their charge is all the time. And so the charges that we know all the time are called fixed charge metals. And there's basically like 2 sections, all right? The 2 sections with these fixed charge metals are groups 1A and 2A. That's like one big section. And then there's also what I'm going to call the stairs, and I'll talk about that in a little bit. Most of the time, at least for groups 1A and 2A, the charge equals the group number. So if you've ever been curious about sodium and what it can do, all right, sodium is a group 1A metal. It's number 11 on the periodic table, but the important part is that it's group 1A. Remember, the periodic table we're using in chemistry has a 1A on the left and 2A right next to it. 3A begins over under boron, number 5. It's also sometimes known as group 13, etc., etc. So magnesium is in group 2A. That's why magnesium likes to be positive 2. And sodium in group 1A, like I said, likes to be positive 1. But everything in those groups is going to be the same. So above sodium is lithium. Lithium, a group 1A metal, positive 1. And below sodium, potassium, K. Potassium also likes to be positive 1. Same thing with group 2A. Magnesium, right above it, is beryllium. Beryllium likes to be positive 2. Right below magnesium is calcium. Calcium likes to be plus 2. So anything in group 1A is going to be positive 1, and anything in group 2A is going to be positive 2. Hydrogen is usually listed in group 1A, and often hydrogen is plus 1. We're going to see that hydrogen's kind of funky sometimes. It does more than one kind of thing. But for this argument, and more often than not, hydrogen is plus 1 too. Now, on the stairs, which I'm going to show here in a little bit, you have to know which of the stairs you're on. But you can probably see that aluminum, gallium, and indium are all plus 3. Zinc and cadmium are both positive 2, and silver is plus 1. So these metals, you always know their charge, and that's really nice. There's no exceptions. So sodium's not going to be plus 2, magnesium's not going to be plus 1, aluminum won't be plus 2, etc., etc. Predictable charges is what fixed charge means. All the other metals, though, on the periodic table, and there's a lot of them, all right? We only talked about groups 1A, groups 2A, and those 6 elements in the stairs. All the other metals, which is all the transition metals, it's all the lanthanides, it's all the actinides, and there's actually quite a few metals under the nonmetals, if you draw in the metalloid line. All of those are what they call variable charge metals, and it's really difficult to know what their charge is going to be. You could ask me what the charge is on some random iron atom, and I wouldn't know. You have to have some kind of way to convey the information to other chemists. So scientists use a Roman number to represent the charge. So if you had an iron plus 2, for example, iron's a transition metal, so it's an unknown, unlike the last ones, you would write it as iron Roman numeral 2 ion. And that's important because there's also a very common iron plus 3. That would be iron Roman numeral 3 ion. And you can see there's a vanadium 3 plus, which would be vanadium 3, etc., etc. Now notice that the ones under the fixed charge metals didn't have the Roman numeral. The Roman numeral is only for the metals that are outside of groups 1A, groups 2A, and the stairs. But if you have a metal in there, you have to tell the other chemists what charge is on the metal, because there are different kinds of charge. If you've seen references to ferrous and ferric compounds, which are iron, or maybe cuprous and cupric, or chromis and chromic, or something like that, that's an old way of representing different charges. But I do not want you using those in my class. Ferrous and ferric and cuprous and cupric and all those things are really lame, in my opinion. And I can talk about this with you sometime if you're curious away from here. But for right now, use the Roman numerals. And again, use Roman numerals anytime you have a metal which is not in group 1A, group 2A, or the stairs. Those fixed charge metals are predictable. The variable charge metals are not predictable. So you need to tell the other chemists what's going on. Let's say that you had a barium and you wanted to know exactly what the charge was on it. That's a really good question. Now, barium on the periodic table has number 56. Z is the atomic number. So you can look at number 56 and tell what it is. So the question, you have a barium -2, barium -1, +1, +2, and the Ba2, which is a diatomic barium. Now, first of all, if you're talking about barium, all right, it's a metal. It's to the left of the metalloid line. So we know that barium is going to be positive, all right? It's not going to be negative. We're going to see the nonmetals are negative. But most importantly, barium is a group 2A metal. So that means it's a fixed charge metal. And we always know what their charges are. So because it's in group 2A, which is one of the groups up here that we know, that means that barium's going to be a +2. And barium, anything, barium chloride, barium sulfate, barium fluoride, whatever, all of those are barium +2. Barium does not really like being +1. It certainly won't be a negative charge, and I've never heard about a diatomic barium, Ba2. The diatomics are the have no fear of ice clear brew, and those are important, but barium is certainly not one of them. The stairs are really interesting. It's a group of 6 elements that have very fixed charges. They're almost always this way. And you can see if you use your imagination, it is like a stairway. Silver is Ag, that's the first step, and it's a +1 metal. Then you take a step up, and the second step, which has 2 steps in it, if you will, is a zinc 2+ and a cadmium 2+. So the elements in the second step are +2. Then you take one more step to the third step, and you've got aluminum, gallium, indium, and those are all +3. So these 6 elements are considered fixed charge metals, just like groups 1A and 2A. Groups 1A are +1, groups 2A are +2, and these are either +1, +2, or +3. Group 3, all right, has boron above aluminum, and below indium, you have thallium, Tl, and those are not fixed charge. Those are a little bit more random. But at least for these 6, you can say that, yep, you always know their charge and stuff. So just kind of realize groups 1A and group 2A and these 6 stairs metals have fixed charges, and you always know what they're going to be. The nonmetals are really important to chemists, and nonmetals have fixed charges, but fixed nonmetal negative charges, and that's going to be really important. So the nonmetals, if you look at these are some of the representatives from that upper right corner, and the way to figure out what the negative charge is you take the group number and you subtract 8. All right, so this is using the A version of the periodic table. So that means fluorine is in group 7, oxygen's in group 6, etc., etc. So to figure out the charge, fluorine is in group 7. 7 minus 8 means that F-1 is the common ion, the anion that you see from fluorine when it gains electrons. But notice here we changed the name, and this is real common in chemistry. The negative ion almost always gets an IDE ending. So fluorine becomes fluoride, and chlorine becomes chloride. You can see that oxygen in group 6, 6 minus 8, -2. So oxide is oxygen with a -2. Going one to the left, nitride comes from nitrogen, and that's 5, group 5 minus 8, -3. If you've heard about like carbide drills, carbide is carbon, group 4, 4 minus 8, it's a -4 carbon. Not as common, but still kind of interesting. Also, if you hear that IDE ending, you know you've got something negative, and that's going to be important to us later on. So on the periodic table, there's fixed charge metals, group 1A, group 2A, and the stairs. There's variable charge metals, which is basically all the metals outside of the 1A, 2A, and stairs. And then you've got the non-metals. Group number -8 is how you figure out their name. But do give the non-metals an IDE ending. Let's say we wanted to figure out what the probable charge is on a phosphide ion. All right. Well, phosphide has an IDE, so it's negative. And phosphide, you might be able to imagine, comes from one of the elements, phosphorus. Phosphorus is under nitrogen, and both of those are in group 5. So the charge on the phosphide will take the group number 5 minus 8. Phosphide is going to be P-3. If you hear phosphide, that means it's a phosphorus with 3 extra electrons. Phosphide has a -3 charge. Kind of overview of what's going on. There are the fixed charge metals, 1A, 2A, and the stairs. Everything in group 1A is +1, everything in group 2A is +2, and the stairs are +1, +2, or +3. And they're all positively charged, all right? There's no negatives. And the magnitude most of the time equals the group number. That's not necessarily the case for silver, zinc, and cadmium, but the other ones it works pretty well. Now, groups 5A, 6A, and 7A are the nonmetals, and those are always going to be negative, and you take the group number -8. Now, that would also include, of course, carbon is carbide, but most of the time this works pretty well. So they're fixed charge nonmetals, and that's going to be important to us. All the other metals, though, are variable charge metals, and they're difficult to predict. So if you ask me, for example, what's the charge on a titanium atom? All right, even me with my PhD, I couldn't tell you, all right? I can tell you more likely possibilities than others, but I can't tell you definitively. Like if you ask me sodium's always +1, all right? Unless you're in a lab or a black hole or next to the sun or something, but sodium is +1. Titanium, though, titanium's kind of all over the place, so that one's harder to tell. So we know that the variable charge metals will be positive, but we'll use a Roman numeral then to represent the charge on the metal. In addition to what we've looked at so far, which I would call monatomic ions, which means single atoms with a charge, single atomed ions, there is a group of what's called polyatomic ions. Poly means many, many atomed ions. These are just groups of atoms with a charge, more often negative, but occasionally positive too. And these, unfortunately, are super common in chemistry. Now, if you look at these lists right here, like here's fluoride and there's iodide. So fluorine to fluoride, iodine to iodide. But wait, there's cyanide. Cyanide is a polyatomic ion. It has a C and an N, and those two come together to have a -1 charge. So cyanide is not carbon or nitrogen. It's both of them together with a -1 charge. Here's hydroxide. We're going to talk a lot about hydroxide. Hydroxide is an O with a oxygen with a hydrogen and a -1 charge. Hydroxide is really common. And there's a bunch of these. Here's acetate. That's one that we'll run into quite often. NO3, -1 is nitrate. So a nitrogen, 3 oxygens, and a -1 charge. Permanganate is fairly common. Carbonate, carbon, oxygen, 3 oxygens, and a -2 charge. Phosphate on the bottom. There's lots of these, gang, and you've kind of got to know them. Notice here how the darker black kind of bolded ones are what they consider here to be more common. All right, that's somewhat accurate, somewhat inaccurate, but still it's a place to start. In a face-to-face class, I will, depending on what you're taking right now, I would give you quizzes or exams where you'd have to know/memorize these. And I do encourage you, regardless of your learning situation, to kind of commit these to memory. We're going to run into them all the time, and not having to look up nitrate is NO3 -1 is going to take a lot of time. Even with the powerful Google, you're still going to have to type it in or voice it or whatever mechanism you use for Google and stuff. So it's really cool to memorize them. In the old days, I would use a flashcard. On one side of the flashcard, I would write nitrate, and on the other side of the card, I would write NO3 -1. So you need to know the name, and you need to know the types of atoms and the charge associated with it. And if I was waiting for the bus or something like that, or waiting at my friend's house, I would just flip through them. Kind of, this is what I did then. They, of course, have flashcards now online. You can look at on your phone or your computer and stuff like that. But the more time you spend with this, the better. They're going to run into to them quite a bit, I'm letting you know. Here's a little bit more thorough list. And there's lots and lots of these, as you can see. One of the few positive ones is NH4 with a +1. It's called ammonium, and ammonium is related to ammonia, which is NH3. I told you to know/memorize ammonia in a previous lecture. Ammonium is also important. You can see that there's like a +1 hydrogen connected to ammonia to make ammonium, or you take away that H+ to make ammonia from ammonium, either way. But anyway, this is just a little bit longer group. In the Chem 221 nomenclature lab, that's the definitive list, if you will, of polyatomic ions to know/memorize. There are a gazillion, nice science word, I know, but there's literally a ton of these crazy polyatomics out there. And again, the more familiar you are with it, the better. And so this is a good reference. The one in the lab is a better reference. Please make sure you know about that. Down here is a note. If you see something that ends in ATE or ITE, that usually means that it's an oxygen-containing anion, or an oxygen-containing polyatomic ion. So if you look, like here's ATE phosphate, all right? Here's 8 in nitrate and also ite in nitrite. So 8s and ites usually, all right, mean that there's an oxygen in it. There are some exceptions, but that's a pretty good kind of overview of some of these. So that's another little hint here to figure things out. Which of the following polyatomic ions probably does not contain oxygen? Okay, so remembering earlier how the 8s and ites, if you see that ending, that usually means that you've got oxygen. So phosphate, that's got ATE at the ending, that's got oxygen. Hypoiodite is the next one, but it has an ITE ending, probably going to have oxygen. Selenate, ATE, you bet. Nitrate, ATE, you bet. But cyanide. Cyanide does not have an 8 or an ite ending. So like we talked about earlier, cyanide is CN-1. There's no oxygen in it. So again, often an ATE or ITE ending or suffix indicates oxygen. Phosphate is phosphorus with oxygen. Hypoiodite is an iodine, I atom, with oxygen. Selenate is selenium. Nitrate would have nitrogen, but cyanide does not have any oxygen, no ATE or ITE ending. Another way to learn the polyatomic ions is to use the little expression related to Nick the Camel. And the expression is, Nick the Camel brat ate icky clam for supper in Phoenix. And you're like, okay, that sounds pretty disgusting. And you're probably also like, what exactly is the purpose of this, Dr. Russell? And I totally understand. It is an acronym. And each of those phrases, Nick, Camel, Brat, Icky, Clam, Supper, Phoenix, has a meaning. Now, a consonant in the English language is not a vowel. And the vowels are A, E, I, O, U, sometimes Y. So if it's not A, E, I, O, U, it's considered a consonant. So notice here in Nick, you have 3 consonants. N, C, and K are not vowels, but it does have one vowel. So the number of consonants equals the numbers of oxygen, and the number of vowels is the charge. So Nick has 3 consonants. It's got 3 oxygens. The I is the single -1 charge, and the N is the nitrogen of nitrate. So nitrate is NO3 -1. Now, camel has 3 consonants, C, M, and L. It has 2 vowels, A and E. So C is carbonate, carbon with oxygen, all right? That means CO3 for 3 consonants and a -2 charge because of the 2 vowels. And you can keep going through and see how all of these work. If you want to go really crazy, maybe Nick had crepes for dessert. Crepes is chromate, another one we'll run into sometimes. Now, this is totally an optional thing to use. Some people love Nick the Camel, and some people think it's really silly. And I don't care which camp you're in. Right? You can think it's cool or silly, and I'll still am very pleased to have you in my class. However, if it does help, this is something that has been useful in the past. Check it out. Little practice with it, and it will rock you pretty well. But again, I was always more of just a memorization person with my flashcards. But anyway, I'm nerdy chemist, so what do you expect? Here's some examples of the importance of polyatomic ions. Nitrate is NO3 with a -1 charge. And we're going to see that nitric acid, which maybe you've heard of before, which is a real common and powerful acid, is basically nitrate with an H+. And acids oftentimes have an H+, maybe even 2 H+s connected to them. So nitric acid loves to get rid of that H+, and this is the acidic hydrogen, by the way. And when it does, it makes nitrate. So nitric acid and nitrate are related to each other. There's a lot of nitrate in the world. There is quite a bit of nitric acid, but not as much of nitrate. Nitric acid loves to give up the H+. So acids will have this hydrogen, which is acidic. And notice that this hydrogen is listed first. That's a way to show other chemists the importance of that hydrogen because it's acidic. Other examples of this, NH4 we saw was ammonium, all right? And NH3 we saw earlier was ammonia. And this is another important combination you've got to know about. Now, ammonia, NH3, reacts readily with water to make ammonium hydroxide. Now, ammonium hydroxide has the ammonium, NH4+, as well as a hydroxide. Hydroxide is another polyatomic ion. So it's easy to go from ammonia to ammonium, or ammonium back to ammonia if you know what you're doing. And it's another thing that shows the importance of acids, the H+. Adding H+ or taking away H+ makes one or the other. But for right now, the important thing, ammonium is one of the few positive polyatomic ions, or cations, we're going to look at. And it is different than ammonia. Ammonia, you have to add an acid, H+, to make ammonium. Here's some other ones. Phosphate, PO4, with a -3 charge. Phosphate shows up a lot in biology. Acetate, which is used for lots of things, is a CH3CO2-1. This is the picture of acetate. This is the CH3. Here is the CO, and then this is the O- part right there. It's the acetate. Finally, on the right side, you've got sulfate and sulfite. And I put these up here because the ATE, polyatomic with an AT ending, that's the most common form of sulfur with oxygen. Sulfate is actually pretty common. And sulfate, sulfur with 4 oxygens and a -2 charge. However, you do run into, or people will use in their day-to-day life, the version with 1 less oxygen, which is called sulfite. So you can see there going from sulfate to sulfite, it's basically 1 less oxygen. You still have the sulfur central atom, you still have a -2 charge, but sulfite has 1 less oxygen than sulfate. And this is a common kind of a pattern you're going to see. Sulfate, sulfite, 1 less oxygen. Now, phosphate and phosphite are also compounds that exist. Phosphite, if you were going to make it, that would be PO3 with a -3 charge. Same charge, by the way, -3, 3-, same thing. Same central atom, phosphorus, but this one then would be phosphite. PHIT. Sorry, my pen doesn't work sometimes super well. So phosphate, 1 less oxygen. So it's not that it means that 8s always have 4 or something like that, or the charge, it's a relative reference. Explore this a little bit, you'll see what I mean. Nitrate and nitrite, similar kind of things. Again, same central atom, nitrogen, but 8 more than ite. So 8 has 3 oxygens in this case, and ite has 2. Notice on the last examples that phosphate, phosphite were 4 oxygens to 3 oxygens. The 8 to ite just means you have 1 less oxygen. It doesn't mean you start with 3 or 4 oxygens. You have to know more about it. And that's where Nick the Camel thing pops in. On the bottom here, we've got another way. This is the blue box is the 8, and that's the most common of the polyatomic ions with that central atom. And as you remove an oxygen, you go to the ITE. So chlorate, you can see in the kind of bluish box, goes to chlorite. Now, once in a while, you can even have 1 less oxygen. So if you take away 1 oxygen from chlorite, you make hypochlorite. So notice the chlor part in the middle is the same here. You're just going chlorate to chlorite to hypochlorite. And once in a while, you can add 1 more oxygen to the common form. And chlorate plus 1 more oxygen would be ClO4 -1. That still has the chlorate base, but you put a per in front of it. So perchlorate would have 1 more oxygen than chlorate, while chlorite 1 less oxygen, and hypochlorite 2 less oxygen. On the website or the companion, if you have it, there's a common polyatomic ions and their corresponding acids handout. It talks more about Nick the Camel and also how you can relate Nick the Camel to acids. And I do recommend that you check that out if you have nothing else better to do. Try not to shoot the instructor, all right?
When metallic zinc is mixed with powdered sulfur and ignited, a powerful reaction takes place that produces zinc sulfide, a compound containing only sulfur and zinc.
This is an example of how you make a compound from the ions. And zinc sulfide, which is ZNS, comes from zinc plus 2. Zinc is one of the stairs, if you remember back there. And sulfide, which is sulfur with a -2 charge. Sulfur is group 6, 6 minus 8. Sulfide has a -2. All compounds, at least in this section, are going to be neutral. They're not going to have any positives or negatives left over. So +2 zinc combined with -2 sulfide makes perfect. +2 goes to 0. Zinc sulfide is neutral. So compounds need to have an equal number of positive cations and negative anions. And we're going to see you'll have to change the numbers sometimes of the cations or anions to make the compound neutral. But neutrality is the name of the game. In the real world, oxygen and water are all around us all the time, and both oxygen and water will mess with, if you will, the positive and negative ions. We'll talk about this in future lectures. So for right now, the most stable kind of compounds are the ones with neutral charges, and we're going to really try hard in this section to make all the positive charges balance the negative charges.
When sodium and chlorine react, the sodium transfers an electron to the chlorine, forming oppositely charged ions. Although the compound has no net charge, its component ions of opposite charge attract each other to form ionic bonds. In turn, these ions are attracted to others, and an ionic solid called a crystal lattice is created.
When you have table salt, that's positive sodium, group 1A sodium likes to be +1, and chloride, group 7 chlorine, 7 minus 8, chloride likes to be -1. So 1 sodium, 1 chloride come together to make NaCl, table salt. In the real world, though, it's not individual sodiums and chlorines. You actually have a whole bunch of different atoms in together. And that little picture there shows what's called the Ionic lattice, which is an alternating chlorine, sodium. And the positive, negative charges aren't just like between each atom, they're between all the different atoms. So this distributed positive, negative charges makes a very stable kind of orientation in space. And a lot of crystal structures come from these positives and negatives kind of making really strong pieces with each other. This is another example of that process. This is ammonium chloride. So ammonium polyatomic ion, NH4 with a +1 charge, that's going to need 1 chloride, chlorine 7 minus 8, -1 chloride. So NH4Cl we'll call ammonium chloride. But in the real world, it's alternating. You can see like here's an ammonium, here's an ammonium, and here's an ammonium. And then in between them, you've got these kind of gold chlorides. And they go kind of left and right and up and down and forwards and backwards. Very, very strong interactions. And we're going to see this is pretty important stuff when it comes to making molecules and also sustaining life. These compounds made of positive and negative charges are called ionic compounds, and they're very strong. And the name of the game here is you just want to make sure you have a neutral compound, which means equal positives and negatives. So if you wanted to make calcium with fluoride, which is calcium fluoride. Well, calcium group 2A likes to be +2. Fluorine, which is group 7, 7 minus 8, -1. Fluoride likes to be -1. And to make this compound neutral, you have to have 2 -1 fluorides to balance that +2. You can think about the calcium as wanting to shake hands with both of its hands, but fluoride only has one hand to shake. So you're going to need a second fluoride to make it balance. So calcium fluoride, CaF2. You've got to have the positives balance out the negatives. So you can think about it then almost as having like 2 fluorides to make that CaF2 molecule. Magnesium is a group 2A metal like calcium, and it likes to be +2. And magnesium, a fixed charge metal, always +2, which is nice. Now, nitrate is a polyatomic ion. It's NO3 with a -1 charge. And polyatomics are just like fluorides above. You've got to have the positives and negatives balance out. And because nitrate has only a -1 and magnesium has 2 positive charge, all right, you're going to need 2 nitrates. So magnesium nitrate, which is what happens when magnesium and nitrate come together, you have to have 2 nitrates, 2 -1s to balance that +2 magnesium. So notice the formula there, Mg parentheses NO3 parentheses 2. If there is more than one polyatomic ion, you can use parentheses like that. Don't use parentheses for anything else, but for more than one polyatomic, parentheses are absolutely cool. So M and G parentheses NO3 parentheses 2 means 2 nitrates for every 1 magnesium. And now you know why that is. Nitrate's -1, magnesium's +2. Got to have 2 -1s to balance that +2 charge. Iron is a variable charge metal. All right, earlier we talked about iron +2 as iron Roman numeral 2, and we also talked about how iron can be +3. So when iron is +2 and it reacts with phosphate, which is -3, notice here this combination. Again, neutrality is the name of the game. So what I would do is take the 2 and the 3, the charges on the iron and the phosphate, and you can take those two numbers and find the common denominator, which means multiply them together. So 2 times 3 is 6. And if you take that common denominator and divide it by the charge, you've got 6 divided by 2, 3, and 6 divided by the 3 of phosphate, 2. So that tells you that you're going to need 3 irons for every 2 phosphates, or 3 times +2 for the iron plus 2 times -3 for the phosphate equals 0. And that's a cool way to think about it too. So iron 2 phosphate, which is how you'd write that, 3 irons and 2 phosphates. And again, notice the Roman numeral reflects the charge on the iron, not the number of irons, and that's important. FePO4 would be iron 3 phosphate. You would have an iron +3 and a phosphate, which is -3. They would come together what I call 1-to-1, +3 to -3, or 3 minus 3 equals 0. Iron 3 phosphate, quite different than iron 2 phosphate. Just be careful of that. The Roman numerals, super important.